Every single day, we're sharing billions of pictures. Everything from that last family vacation to, really sensitive medical scans. But have you ever stopped to think about how we keep all that data safe? Well, we're about to dive into the absolutely fascinating science of how it's done. And it's this incredible mix of beautiful, complex math and some seriously cutting-edge AI. So here's the roadmap for this explainer. We're going to start with the problem itself. Then we'll get into this wild idea of using chaos theory as a solution. We'll look at how that chaos actually scrambles the pixels, how AI comes in to make it even stronger, and then we'll see the final recipe. And finally, we'll talk about why this is so important for all of our digital security down the road. All right, so let's dive right into the core challenge here. We've got this enormous amount of visual data we create every day, right? So we need a way to take a priceless memory and turn it into what just looks like random noise, and we need to do it super fast and efficiently. Just look at this. On the left, you've got a perfectly clear photo, and on the right, that same image is just complete static. The billion-dollar question is, how do you build a system that can do that flawlessly? And then, and this is the really important part, reverse it perfectly so that only the right person can ever see the original. Well, the thing is, a lot of the old-school encryption methods, they just weren't built for the world we live in now. With massive image files and all these little low-powered devices. They can be super heavy, they drain your phone's battery, and they slow everything down. Plus, there's this huge threat looming on the horizon, quantum computers, which could, one day, just crack our current codes like they're nothing. Now, here's where it gets really cool. The solution comes from a place you would probably never expect. The beautiful, mind-bending field of mathematics called chaos theory. Now, chaos theory isn't about total randomness, not at all. It's about systems that actually follow very specific rules, but they're incredibly sensitive to where they start. You've probably heard of the butterfly effect, right? The idea that a butterfly flapping its wings in Brazil could kick off a tornado in Texas. That is the core idea right there. Tiny, almost immeasurable changes at the beginning can lead to massive, totally unpredictable results later on. And this image right here, it illustrates that idea perfectly. This is the Lorenz attractor, probably the most famous picture of a chaotic system. See how that path just loops and swirls, but it stays within a certain shape? It's got structure, it's contained, but you can never, ever predict exactly where that point is going to be in the future. It is beautiful, ordered, and completely unpredictable all at the same time. And that right there, that's the secret sauce. This exact quality, predictable rules that lead to unpredictable results, is the perfect ingredient for encryption. It lets us create these incredibly complex, random-looking security keys without needing a supercomputer to do it. Okay, so how do we actually take this beautiful idea of chaos and apply it to a picture? Well, the tools we use are called chaotic maps, and they're basically the mathematical engines that do all the scrambling. You can think of each of these maps as a unique secret recipe for shuffling pixels. Every single one of them, from the Arnold cat map to the Lorenz system, uses a different set of math equations to take that original grid of pixels and just rearrange them into a jumbled, unrecognizable mess. But, and this is important, not all of these recipes are the same. As you can see here, different maps have different trade-offs. The Logistic map, for instance, it's pretty fast, but its security level, which we measure as entropy, basically how random it looks, is just okay. The classic Lorenz system gives you high security, but it's a bit slower. But then you get something like the 4D Lorenz system, which, by adding this whole other dimension of complexity, manages to be both incredibly fast and super secure. I mean, this chart just makes it totally obvious. Look at the difference in those encryption times. The older maps are chugging along, but the 4D Lorenz system is practically instantaneous. That's a huge leap forward. It gives us the best of both worlds, serious speed and rock-solid security. So using chaos to shuffle pixels is a fantastic starting point. It's really good, but it's not perfect. If an attacker could somehow figure out the exact recipe and the starting key, they could undo it. So to make it truly next level, researchers brought in a powerful partner, artificial intelligence. Specifically, they use a kind of AI called a convolutional neural network, or a CNN. Now, CNNs are brilliant at finding and learning complex patterns in pictures. So in this setup, the CNN acts like an expert codemaker. It takes the image that's already been scrambled by chaos and then performs a second, way more complex transformation on it. It learns the absolute best ways to further mix up all that pixel data, making the final encrypted image way, way harder to crack than just the chaos step alone. Okay, so let's put it all together. Let's look at this final recipe that combines the elegant unpredictability of chaos with the smarts of AI. All right, let's walk through this whole workflow. It starts at the top, right? The chaotic system spits out a secret key. That key is then used to do the first big scramble of the original image. But we're not done. That scrambled image then gets fed into the AI network, and that's the deep encryption stage, which gives us our final super secure cipher image. It's a really powerful two-stage process. Chaos brings the speed, and the AI brings the heavy-duty, robust security. So to break it down, it's a simple but really powerful three-step dance. Step 1, the 4D Lorenz system makes a super complex key. Step 2, that key shuffles all the image pixels. And step 3, the AI model adds that final deep layer of encryption. It's security built on top of security. And boom, this is the results. You go from the crystal clear original image on the left to what looks like complete and total static on the right. Every bit of that original visual information is completely hidden, protected by this tag team of chaos and AI. Now, this isn't just some cool experiment stuck in a lab. This hybrid method has really big implications for how we protect our data in the real world. Just think about it for a second. Yeah, this can protect your vacation photos, but it can also protect something incredibly sensitive, like an MRI scan. For that kind of data, you need encryption that is not only crazy strong for patient privacy, but also fast enough that it doesn't slow down the doctors who need to see it. And because it's so efficient, it's perfect for all those little smart devices in our homes. And maybe most importantly, its complexity makes it a really strong contender for protecting us against future attacks from those quantum computers we talked about. So the main takeaway is this. Traditional methods are great, they're the foundation of security today. But this hybrid approach is a really significant step forward. It's built to be faster, more efficient, and more resilient. It's a security solution designed for the challenges that are coming our way. It's a pretty fascinating thought, isn't it? As our digital lives get more and more complex and the threats get smarter, the answer to keeping our privacy safe might not come from bigger, stronger, more rigid systems. It might just come from harnessing the elegant, beautiful, and infinite complexity of chaos itself.